An 80% power factor generator delivers 80% of its maximum real power, measured in kilowatts, for a given apparent power, measured in kilovolt amps. The remaining 20% is consumed as reactive power, measured in kilovolt amps reactive, which does not perform useful work. When an inductive load, such as motors or transformers, is connected to the generator, the load draws additional reactive power, further reducing the power factor. To compensate, capacitors are connected in parallel with the load to provide reactive power and improve the power factor. Not using a capacitor bank has consequences. Firstly, reduced generator efficiency. The generator will have to work harder to deliver the same amount of real power, resulting in increased losses and reduced fuel efficiency. Secondly, increased line losses. The higher reactive power flowing through the wires increases the impedance of the lines, leading to higher power losses. Thirdly, potential for voltage instability. A low power factor can cause voltage fluctuations, which can damage equipment and disrupt operations. It is possible for the power factor on the secondary side of the transformer to be lower than 80% the generator's power factor. This can occur firstly if the transformer has a low power factor due to resistance and reactance losses, and secondly if there is additional inductive load on the secondary side, such as motors or transformers, which draw reactive power. Using a capacitor bank for power factor correction is essential, even with an 80% power factor generator. It helps improve generator efficiency, reduce line losses, maintain voltage stability, and prevent potential damage to equipment. In greater detail, the power factor is a measure of how effectively electrical power is being used. A power factor of 1.0 or 100% indicates that all the power supplied is being used for useful work. A power factor of less than 1.0 indicates that some of the power is being wasted. Reactive power is the portion of electrical power that does not do any useful work. It is caused by inductive loads such as motors and transformers, which create a magnetic field that stores energy. This energy is then returned to the power system, but it is out of phase with the voltage. This out-of-phase current is what causes reactive power. Capacitors are devices that store electrical energy. When connected in parallel with an inductive load, they provide reactive power that is equal and opposite to the reactive power drawn by the load. This cancels out the reactive power, improving the power factor. The amount of reactive power that a capacitor bank must provide depends on the size of the inductive load and the desired power factor. Capacitor banks are typically rated in kilovolt amps reactive. The size of the capacitor bank should be chosen to bring the power factor up to at least 0.95. The benefits of power factor correction include reduced energy costs, increased system capacity, improved voltage regulation, and reduced equipment wear and tear. Reduced energy costs happen because power companies often charge customers with low power factors a penalty. By improving the power factor, customers can reduce their energy bills. Increased system capacity results from improving the power factor, freeing up capacity on the electrical system. This can allow customers to add more loads without having to upgrade their electrical infrastructure. Improved voltage regulation from a higher power factor can improve voltage regulation, which can help to prevent equipment damage. Reduced equipment wear and tear from a better power factor, reducing the stress on electrical equipment, which can extend its lifespan. There are several factors to consider when selecting a capacitor bank. These include the size of the inductive load, the desired power factor, the voltage of the electrical system, and the environmental conditions. Capacitor banks are available in a variety of sizes and configurations. They can be installed indoors or outdoors. They can be manually switched or automatically switched. The type of capacitor bank that is best for a particular application depends on the specific requirements of the application. Power factor correction is an important part of electrical system design. By improving the power factor, customers can reduce their energy costs, increase system capacity, improve voltage regulation, and reduce equipment wear and tear. Let's delve deeper into the reasons why a capacitor bank is crucial even with the generator already operating at an 80% power factor. We'll explore the implications of inductive loads, reactive power, and the benefits of power factor correction in more detail. Consider an electrical system powered solely by an 11 kV, 50 Hz generator, which feeds an 11 kV primary to 480 or 277 V secondary transformer. The generator has a power factor of 80%. The power factor, often represented as cosine phi, is the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amps. It indicates how effectively electrical power is being used. An 80% power factor means that only 80% of the apparent power is being used to perform useful work, while the remaining 20% is reactive power, measured in kilovolt amps reactive, which circulates in this system without doing any real work. This reactive power is primarily due to inductive loads, such as motors, transformers, and fluorescent lighting ballasts. Inductive loads create a magnetic field to operate, and this magnetic field causes the current to lag behind the voltage, resulting in reactive power. Without power factor correction, this reactive power has several negative consequences. Firstly, increased current flow. Reactive power increases the total current flowing through the system, including the generator, transformer, and cables. This increased current leads to higher losses due to the resistance in these components, which are proportional to the square of the current, I squared R losses. Secondly, reduced generator capacity. The generator must supply both the real power and the reactive power. The reactive power component reduces the generator's ability to supply real power, effectively diluting its capacity. Thirdly, voltage drop. The increased current flow due to reactive power causes a larger voltage drop along the conductors. This voltage drop can affect the performance of sensitive equipment and may even cause them to malfunction. Fourthly, higher electricity bills. Many utilities charge customers based on their apparent power consumption, measured in kilovolt amps, rather than just real power, measured in kilowatts. A lower power factor means a higher apparent power demand for the same amount of real power, leading to increased electricity bills. Power factor correction involves adding capacitors to the system to counteract the effects of inductive loads. Capacitors store electrical energy and release it back into the system, providing the reactive power needed by the inductive loads. This reduces the amount of reactive power that the generator must supply, improving the power factor and mitigating the negative consequences described earlier. Now let's consider the specific scenario of a generator with an 80% power factor feeding a transformer. The transformer itself introduces some inductive reactance, which further reduces the power factor on the secondary side. If the loads connected to the secondary side are also inductive, such as motors or HVAC equipment, the power factor can drop significantly below 80%. Even if the generator could handle the reactive power demand without a capacitor bank, the voltage drop and increased current flow in the transformer and downstream circuits would still be a concern. Installing a capacitor bank on the secondary side of the transformer can improve the power factor, reduce voltage drop, and increase the overall efficiency of the system. The size of the capacitor bank needed depends on the amount of reactive power being consumed by the loads. A power factor correction study can be performed to determine the appropriate capacitor size. This study involves measuring the power factor and current at various points in the system and calculating the amount of capacitance needed to achieve the desired power factor. The location of the capacitor bank is also important. Ideally, capacitors should be placed as close as possible to the inductive loads to minimize the current flow in the upstream circuits. However, this may not always be practical, and a centralized capacitor bank can be used to correct the power factor for the entire system. There are several types of capacitor banks available, including fixed capacitor banks and automatic capacitor banks. Fixed capacitor banks provide a constant amount of reactive power, while automatic capacitor banks adjust the amount of reactive power based on the load demand. Automatic capacitor banks are more expensive but offer better power factor control and can prevent overcorrection, which can also be detrimental to the system. In conclusion, even with a generator having an 80% power factor, a capacitor bank is still essential for power factor correction. It improves generator efficiency, reduces line losses, maintains voltage stability, and prevents potential damage to equipment. The size and location of the capacitor bank should be carefully considered based on the specific characteristics of the electrical system and the loads being served. Remember that while an 80% power factor might seem acceptable at the generator, the power factor can degrade further down the line due to transformer reactance and inductive loads on the secondary side. Therefore, power factor correction is a crucial aspect of ensuring efficient and reliable power delivery. Furthermore, consider the long-term benefits of implementing power factor correction. While there is an initial investment in the capacitor bank, the savings in energy costs, reduced equipment wear and tear, and improved system performance can quickly outweigh the initial cost. Power factor correction also contributes to a more sustainable energy future by reducing energy waste and improving the overall efficiency of the power system. It's not just about meeting the minimum power factor requirements of the utility company, it's about optimizing the electrical system for maximum efficiency and reliability. Also remember that regular maintenance of the capacitor bank is important to ensure its continued performance. Capacitors can degrade over time and their capacitance can decrease. This can reduce their effectiveness in correcting the power factor. Regular inspections and testing can help to identify and replace any faulty capacitors. Finally, consider the impact of power factor correction on the harmonic content of the electrical system. Capacitors can sometimes amplify harmonic currents, which can cause problems with sensitive equipment. Harmonic filters may be needed in some cases to mitigate the effects of harmonic currents. In summary, power factor correction is a complex but essential aspect of electrical system design. It requires a thorough understanding of the characteristics of the electrical system and the loads being served. A well-designed and maintained power factor correction system can provide significant benefits in terms of energy savings, improved system performance, and reduced equipment wear and tear.